All right, let's get this party started. All right, happy Friday. We're going to start on rotation. This is going to be not happy Friday, man. She started shaking her head no real quick. Um, Happy Friday. We've got just one class to get through, and then we're going to be on the weekend. We're starting rotation. Today will be rotational kinematics. So we're going to take stuff that we don't quite know rotation. We're going to apply it to something that we do know kinematics. Each day it's going to be something different. This will have its challenges because it's the first time we talked about rotation, but it'll have its comfort knowing that we know kinematics. We're just going to apply it to rotation. You know, things turning around, things spinning. So let's do that. I'm going to start out with some notes and then go from there. So let's go to a page where I can write. All right. For those that are wondering, yes, the retests have not been put in yet. Yes, they will be put in eventually, and they'll definitely be put in by end of day Monday, because by then I have to submit grades for IPR. So I'll get them done by IPR, maybe today, maybe tomorrow, maybe Monday, but sometime in between. Let's focus on this kind of stuff. No one really asked, but I just want to get that question out there. All right, what are we talking about? We're talking about rotational kinematics. So let's get this titled up. Rotational kinematics. Yes, I make my third grade teacher proud with my my penmanship. And I don't know how to spell, and there is no spell check here. So if I misspell something, forgive me. You can point at it, you can laugh at it, but just be kind, because it's Friday. You can only be nice on Friday. So when we're talking about rotation, what are we really talking about? We're talking about spinning. We're talking about object rotating in a circle. We're talking about wheels rolling, right? That's all rotation. So it's kind of like, why be scared of rotation other than the teacher said you should be scared of rotation? There's really no other reason. It's just me being mean and trying to make you scared. I'm kidding. I'm not really that mean. Not usually. Sometimes, but not usually. So let's look at this. If we talk about a circle, all right, I can draw a circle. That's my circle. And let's say it's on the ground right there. There's the ground, and it's going to go this way, all right? So,
Teachers, all students in the cafeteria and gym are released to go to their fourth period class. Thank you.
You're welcome. All right. You guys are released to go to your fourth period class. So how far does it go with respect to the number of turns? Or how far it does go is in respect to the number of turns. So if this ball were to rotate, let's see, if I were to write this, if it were to turn one full turn, okay, how far is it going to go? No, seriously, how far is it going to
go? Would that be like the circumference of like the ball?
Yes. Why is it that I sit before 35 Independence kids and I've got a Wakeland student showing you guys up? Yes, it's absolutely got to do with the circumference. If it's a little bitty round thing, it's going to, like a penny, like a dime, it's going to go like that far, right? If we're talking about a big monster truck tire, it's going to go further. So one full turn absolutely has to do with the circumference. And we know the circumference, we can calculate the circumference. How? How do we calculate circumference?
Pi r.
Go for it. It's the Meister. 2 pi r. All right, got it in the chat. Yeah, we got 2 pi r. All right, so then if we did 2 full turns, we know what that would be then, right? Right? 4 pi r. Yes, thank you in the chat. 4 pi r. We can totally do this. So let's create a table real quick. We're going to create a table, talk about the number of rolls, the displacement, and the total angle that we're going to be changing along the way, okay? So let's create that table. It's going to be number of rolls. I'm not talking about dinner rolls here. It's too early for that. The displacement, I'm just going to put DISP for displacement, and then total angle. I always get worried about angle. I think I'm going to write angel, but I think I have it right. All right, so total rolls, displacement, number of rolls, displacement, total angle. And we said, hey, if we've got one roll, if it goes around one full time, all right, the displacement is the circumference, which is 2 pi r. The total angle that is displaced, if you go around one time full around, what's the angle there? Right.
360.
Yeah, go in. You can say it out loud too. I'm pointing at the chat. I see it pop up there. I didn't have that fear until you just said it. Don't have that fear. No, don't have the fear. I mean, yeah, kind of have the fear, but no, don't admit to it. I'm just kidding. Totally admit to it. 360 degrees. We got it? One time around, that's one circumference. That's 360 degrees. This is like I put a dot on my wheel here. See how that picture, I put a dot at the top at like the 12 o'clock. As it goes around, if it were to go around and then stop, we could use a protractor to say, what was the change in angle? It started up here, then it went over there. What's that angle? That's what we're talking about here, okay? Nothing mysterious yet, but stay with me. All right, two rolls we said was two circumferences, which would be like 4 pi r, and that would be, I don't know, 720 degrees, okay? Sounds like it's hot, 720 degrees. Anyway, sorry, bad joke. All right, what about half of a way around? If it went halfway around, what would we say?
Would it go pi r in terms of displacement, and then it would go 180 degrees?
Right, exactly right. You're right there with me. So you got 1/2, which would be pi r, and that'd be 180 degrees. We'll do one more just for kicks because I have those numbers written down. What about 1/6?
60 degrees.
60 degrees, perfect. And then what's my displacement?
1/3 pi r.
Yes, so I'm going to write it as pi over 3, but that is 1/3 pi r. That's totally right. Okay, and this is when we're talking about, when we talk about linear displacement, right? We've done everything, for the most part, what we've talked about is linear, the linear velocity and the acceleration and the displacement either in the X or the Y, but it's all been linear. It's not talked about rotation until now. So when we're talking about rotation, we want to put the total angle, we want to calculate that in radians, okay? Our unit is going to be in radians for our displacement. Instead of 2 pi r, I want to do it in radians, which is not hard because radians is already there. See that r, which is radius? Let's call that radians, okay? So I'm going to make another column, and we're going to just do this based on radians. I know it's a little bit weird, but I tell you, if you stick with me, by the time we get most of the way through the class, I'll get you more confused, and then I'll bring you most of the way back. Promise. All right, radians. There we go. All right, we got radians. So if we said for one rotation, which is 2 pi r, how many radians is that? Well, that would be 2 pi radians. 4 pi r would be 4 pi radians. And this would just be pi, and this would be pi over 3. We're just taking the radius and making that a unit, radians, okay? It's the easiest way to think about it, all right? I'm sure there's much more complicated explanations and way to justify and get to that answer and derive it. I'm just gonna say, take that radius and make it radians, okay? It's an easy way to think about it. What does radians mean? What does anything mean? What is the meaning of life? Why are we all here? I'm just kidding. Radians, think of radians as the radius, but make it a unit. Think of the radius as a unit, okay? That's the easiest way I can describe it. As we use it, it will get more clear, okay? I think that the clarity doesn't come from the definition. I think the clarity comes from the experience using it. It's kind of like, hey, no one ever taught me how to do this. I just did it long enough to where I know what I'm doing. I'm going to try to get you there today. It's part of the unit circle. I know if you guys been in, is it pre-cal that does the unit circle? Yeah, they did that project earlier. I saw a bunch of 3D unit circles in Miss McClary's class, and I saw some really good ones, and I saw some pretty sad ones too. So, you know, everybody's got their own way of doing things. All right, so we've got that. Now for a rolling object, it's linear displacement. I'm going to scroll this up just so I can, actually I can write over here on the right. I'm going to write things that are sort of important. So, but we know for a rolling object, what do I have written down? It's linear displacement. See, there's already people leaving. It's linear displacement, which is defined by, or identified as delta x, you know, the change in the x position. The linear displacement depends on the angle that the object moved through. For a rolling object, its linear displacement, how far it moves from its starting to its ending position, depends on the angle that the object moved through. That being said that way, let's create a formula where we can say that delta x, the linear displacement, is equal to the radius times the angle. Okay, linear displacement is equal to the radius times the angle. Here we've got r is the radius, delta x is the linear displacement. All right, scroll up a little bit so I've got some room to write. And then theta, it's a pretty, it's the circle with a line through it. I know my penmanship's not the best, but hey, it gets a job done. All right, yeah, they've already been. All right, theta being linear, theta being angular displacement. For it's the angular displacement, that's how much of an angle we turn through. So we could also say it's angle we turn through. Is there any way else we can think of it? How much rotation? So these are just different ways to think about the same thing, okay? Amount of rotation. And here, the unit is radians. The unit is radians. All right, so delta x, the change in the position for a rotating object, for an object in rotation, it's the radius times the angle, gives us the linear displacement. R is the radius, delta x is the linear displacement, and then theta is our angular displacement. We can think of it as the angle that we turn through, the amount of rotation, and the unit that we're using for theta is in radians. It's in radians. Okay, that takes me through the first half of my handwritten notes. I've got the second half is actually shorter than the first half, so I don't know why I call it a half. But I'm gonna shrink this in and I'm gonna erase this and start fresh on this page. So hopefully you've got as much as you needed from this written down. If not, I'll take our recording today and post it either later today or sometime tomorrow. Let's get this cleared out. Like it was never even there. All right, start fresh. So let's go back to stuff that we're used to, okay? Started out talking about a couple of things there that started getting, okay, what is he talking about? Not really sure about this. So let me get back to where everybody should feel good, and that's our linear quantities. The linear quantities. I told you that today the title was rotational kinematics. So I misspelled quantities. Look at that. Ease. Let's see if I erase it and fix it. Is it better? Yeah, it's better. All right, what were our linear quantities when we were looking at kinematics back in September?
Displacement, time, acceleration, velocity, initial velocity.
Okay, perfect. So you said displacement. Ooh, still don't know how to spell. They're gonna send me back to elementary school. Displacement, let's see, you said velocity. I'm gonna keep the velocities together because initial and final velocity, it's still velocities at different points in time though. So velocity, you said acceleration. Acceleration. And you said time. I'm not gonna list time because time's the same for everything. It doesn't matter if we're rotating or moving in a straight line. Time is still, my stopwatch doesn't care. It's still gonna be like click, 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 click. Right, so we've got those things. All right, so if we were to, the variables, let me list those next. That seems like a good idea. We know that displacement was x, velocity was v, acceleration was a. If we wanted to define displacement, what's a way to define displacement with words?
The distance
Change in
from
position.
start to finish,
Change in
Okay.
position.
from start point to end point. There's straight line distance from,
Start to finish. Okay, so you had 5 words. Can someone give me a shorter definition?
Change in position.
Okay, 3 words. Can anybody shorten it beyond that? No, you can't. 3 words is as low as I can go too. So those
Distance
are all
traveled?
correct. I'm just going for sure. What was that?
Distance traveled?
Distance traveled. Well, but if you come back to the same starting point, it's got to be a change. It still has to be, because if you come back to the starting point, there's no change in positions. I like where you're going though. I like where you're going. All these are good. As long as we understand what it is, I'm going to use change in position because it identifies that there must be a change. And it's identifying it is from final minus initial, because we're talking about, we don't care about the path. We just want to know what was the change. In the end, what was the difference? So change in position. Okay, and then what about velocity then?
Speed with a direction.
Speed with the direction. Okay. What I'm going to do here is I'm going to try to find similarities and use it and create patterns. Or we're going to
displacement over time.
Okay. What about if I keep the change in position and then say over time or with respect to time? It is stretching it out, but displacement over time is good and short. I'm just going to use the pattern of the words we've started with. So I said change in position. So now I'm just going to say change in position over time. How about that? So change in position over time. And I want to do this in a way that it just kind of replicates things. So that way it's simplistic. It's easy to review and not change up the word. So if I did velocity as a change in position over time, what's acceleration?
Change in velocity over time.
Exactly right. Change in velocity over time. The change in velocity over. Ooh, I started doing of. Fix that. Over time. And if we put a little formula to these, we can see that velocity would be equal to delta x over t, and then acceleration is equal to delta v over t, right? Want to just kind of keep it simple, straightforward. So those are our linear quantities. That just means there must be something different going on here. We're talking about rotation. Rotation, we said theta was an angle, and that's kind of where we want to go next is I want to compare that to angular quantities. So where we had displacement, now we're going to have angular displacement. And I love patterns. That's why I kind of understand math most of the time. If displacement becomes angular displacement, what does velocity become?
Angular velocity.
Yeah, it does. And what's the next one going to be?
Angular acceleration.
Yeah, it is. This is how we're trying to make something that's complicated, make it a little bit easier. You know, something that makes sense, then the next thing makes sense to the next thing, that sort of thing. Okay, so we did what did we do for linear quantities? We gave them titles, then we gave them variables. So let's give these variables. We already said that angular displacement was theta. Okay, that was on our previous page. Okay, angular velocity, instead of theta, it's a lowercase omega. And what it looks like is a very curvy W. It also looks kind of like a butt, but it's a lowercase omega. And then for angular acceleration, it's an alpha, which looks like that. And the angular acceleration is kind of easy because it sort of looks like a cursive A, just with 2 tails on it instead of 1. So you've got angular acceleration is the alpha, angular velocity, which is the lowercase omega, and then you've got theta for angular displacement. And then if we wanted to give these wordy definitions, how would we define angular displacement?
Change in angular position.
Should I say it one more time?
Change in angular position.
Good. I'm just going to shorten it by one word. I'm just going to say change in angle. Okay. Just to make it simple, it's going to be just a change in angle. Okay. And then that means angular velocity is going to be change in angle over time. And then for the angular acceleration, that would be change in angular velocity over time. Okay, so we've got our definitions. We've got our variables. What do we do next? We put in little formulas, right? So we need a formula for angular velocity. Here, we're going to write it. It's going to be just like for regular velocity, where we can put in our variable. There it is. It's equal to, it will be delta theta over t. And then for alpha, that will equal delta omega over t. Last thing is units. Let's get the units in. And let me change color just a little bit so they stand out. So units. Here are the units for angular displacement. The unit is radians. Remember that column in our chart, very first chart we did? How the unit was radian. When I was like, hey, we're going to use this in radians, it's going to be our units. That's our theta. So as we change our angle, it's going to be, theta is going to be in radians. We'll get experience with it today, I promise. So if that's radians, velocity is going to be radians per second. And that means acceleration is going to be radians per second squared. Sorry. The red one. Now, if we want to move between linear quantities and angular quantities, we do have formulas in order to move between linear to angular. I'm going to give those to you right now. I'm going to put them right down the middle. X, we've already said change in X is radius times theta. Okay, so then we can say that velocity is going to be equal to what? What's the pattern? Velocity is going to be equal to what? How do I get to angular velocity? What do we think?
Radius theta over
Radius to omega. And then acceleration is going to be what?
Radius times angular acceleration, or alpha.
Yep, radius alpha. Exactly right. By setting this up in patterns, it's easy to, if you learn one, you know how your way to get, your way to get through all of them. Okay. Now, one last little bit. I'm gonna give you a second to look at this, make sure that you've caught up to me. If you need to take a screenshot, grab it, whatever. Finish up writing. Let's look at the kinematic equations. Look how they've changed, and then we're gonna do our work. All right. I'm gonna scroll this up. All right, I've got 3 of the 4 kinematic equations written out for me because, I mean, once you see the first one, you're going to kind of get it. But let's go ahead and write these out. So let's go back to purple. And my favorite equation, because it's the easiest one to remember and it's the easiest one to solve for, VOTAT, V equals V naught plus A times T. There's our VOTAT. Then we had V squared is equal to V naught squared plus 2A delta X. We had delta X is equal to V naught T plus 1/2 A T squared, right? Those are 3 of those 4. It's basically, I skipped the trapezoidal one. It still exists. It's just you're going to get the idea and the practice all here. And these are the ones we use primarily, not to say you can't use the trapezoidal one. If we're going to move this from the linear quantities over to the angular quantities, what we can do is we're just going to do a simple replacement. That's all it is. Velocity, v becomes a lowercase omega is equal to omega naught plus alpha times time. So instead of votat, we kind of got a wotat going on. The next one would be omega squared is equal to omega naught squared plus 2 times alpha times theta. The last one would be theta is equal to v naught, which would be omega naught times time plus 1/2 times alpha times squared. It's just simple replacement. It's the same equations all the way across. We're just changing the variables. They work the exact same way. They work the same way. All we have to do is remember, identify our given. Make sure that our units are in the proper units for the equations. Pick the equation, rearrange it, substitute and solve.
Mr. Watley,
What's up?
so you said that like for displacement it's equal to it's x equals r theta, and
Yes.
like velocity equals v equals r omega.
Yes.
So like in the kinematic equation when it says votat, so wouldn't the v have to be replaced by the r omega, because that's what v is defined as?
I like what you're asking, but let me ask you this. If I put an R at each one of these locations, couldn't I then factor out the R in many? Well, the second one, I'd have an R square. I could factor the R out in oh no, I'd have an R square everywhere, wouldn't I? So the first one, it would be omega R equals omega naught R plus alpha RT. Well, then I could just cancel out the R's, couldn't I? And the next one, I would have omega square R square is equal to omega naught square R square plus 2 alpha R theta R. There I could divide by R square. So yes, it would replace with the radius, but then the very first step you would do every time you write the equation is factor out the R's.
Okay, so the r doesn't really matter in the kinematic equations.
Correct. In the kinematic equations, they're not needed. But if you have, you're going to see today, you're going to have velocity and you're going to want rotational velocity. You're going to have your rotational velocity and you're going to want to know what your translational velocity is. You're going to want to move back and forth. And so that's why we have these equations in red up here, because if you've got one, you can get to the other.
So those equations, like we don't have to worry about them for the kinematics.
Correct. The kinematics, it's a simple replacement. And it's a simple replacement because the R will factor out. Because if I was to put the R, let's go to the votat at the top. If I were to put the R in here, the R there, and the R there, I would just simply then divide the whole thing by R and they would cancel out.
Right. Okay. That makes sense.
That's no problem. You know what? And you're the first person out of 70, 80, 90 students I've talked to today that's asked me, well, hold on, you replaced it, but you dropped the R. So I'm glad you're paying attention. And it's good to look through these things so we don't have any confusion later on. So it's a good question.
Thank you.
Absolutely. All right, so I've gotten through the notes that I listed out in my my handwritten notes. Let's go over to the page that's in Canvas and see what it had for our notes there. So I'm just going to rotate this so I can get into it. Here it shows us translation. See how translation's working in a straight line? This is the illustration on your screen. Translation or translational simply means linear. If you see translational, think linear. Think what we've been doing before we got to rotation. Rotation is rotating. And if you put it together, a combination, it's showing that trajectory where it's both spinning and moving forward. Okay, it's just showing it can be combined. It goes through some notes. Most of this stuff we've already talked about, but it's put in different terms. So it's worthwhile going through. Okay, I'm not going to spend a lot of time on it because, well, we spent time on presenting the notes the way that we think is best. Now, here in bold, this part, I like that this is mentioned. Let me get to my drawing tool right here. Notice that your omega must be in radians per second. If you're given revolutions per second or RPM, you got to convert. We're going to do that today, but just know when you see RPM or revolutions, we're going to have to convert that to radians. You're going to see how to do it, but just know that's going to be one of your steps. Okay, just wanted to point that out. Let's get to sample problem. There's a sample problem 1 and a sample problem 2 on this page. We're going to do them both. Then we're going to go to the homework. I'm going to get you like, I don't know, a third of the way to half the way done with it. And I'm going to say, okay, you finish it up. That way you kind of learn through the struggle as well. Let's take care of this. Let's get this done first. All right, Venus takes 225 days to orbit the sun with a nearly perfect circular orbit. What is the angular speed? Angular speed, we know that that is our omega. It's asking us for omega. Okay, now it gives us 225 days. Omega, one thing that we said, that is equal to what? That's a
Radians per second.
Yep, but it's a change in theta over time, right? And then theta would be, it's radians per second. We can call it radians per second. So we have to kind of know where we're going. We have to know what our destination is and then see what we've got. Well, it's asking for angular speed. We know that's a change in theta over time, and time is in seconds. For time, we convert days to seconds. Yes, yes. So they gave us time in days. We need it in seconds. So let's do our dimensional analysis and let's get it there. Won't take but a second. 225 days. Remember, we draw the track. It's been a minute since we've done that, but hey, we can get through it. If days are on the top, we want to get rid of it. You got to put it in the bottom, 1 day. It is 24 hours. All right, and I don't want hours, so it's in the top. I'm gonna put it in the bottom. Let's see, 1 hour. We remember is 3,600 seconds. Okay, if you don't remember, you can do times 60 for minutes and then times 60 for seconds. 60 times 60, 3,600. You can get there. That's fine. It's cool. We all have our ways. When we do this, I got 1.94 times 10 to the 7th seconds. Now, if I did my math wrong, let me know. That's just what I did when I put in the calculator. So now at least I have a time, right? And let's write down the things we know. We're going for our omega, which is our angular velocity. And we know that that is a change in theta over time, right? And then we say, okay, well, let's look back at the question. It said it takes 225 days to orbit the sun with a nearly perfect circular orbit. How many times around is it going?
1.
Yeah, one. It showed up in the chat too. It's going around 1 time. And 1 time in a circle, how many, what would my theta be for that in radians?
2 pi.
2 pi.
Right, it'd be 2 pi radians, right? So I could put 2 pi radians over the time we said was 1.94 times 10 to the 7th seconds. All right, and my unit that I want is radians per second. So there, I've got my unit, radians per second. I can take my calculator, 2 times pi equals divided by 1.94 times 10 to the 7th. When I do that, kind of simplify that math, I get 3.23 times 10 to the negative 7 radians per second. That's the unit I'm looking for, so that's the solution I've got. 3.23 times 10 to the negative 7 radians per second. And that's Venus going around the sun, if it really does take 225 days. I don't know if the question was made up or if they're using factual information, so there you go. I'm going to scroll this up just enough so that I can see what's going on next. Next, it says, what is the translational velocity of Venus? Translational velocity, remember, that's our linear velocity. That's V. And we said that V is equal to the radius times omega. What's the radius? Well, the radius is a distance that they provide us right there. By multiplying by the radius, see the unit up here, radius, that we just used. I'm going to draw an arrow to it, radius. When we replace that unit radius, or radians, with a radius that's measured in meters, that becomes, we're bringing that number in and we're replacing it with meters. We're replacing radians with the radius. And that converts it back to linear. Okay, I know it's weird. I know, stick with me. All right, so we said radius first in our formula, so 4.184 times 10 to the 10th power times 3.23 times 10 to the negative 7 equals, put that in my calculator, I got 13,516.21, and I'm left with meters per second as my unit. That is the velocity of Venus. Pretty fast. Every second, 13,500 meters every second. Could I repeat that again? Absolutely. In the sample problem number 1, we got our angular velocity as 3.23 times 10 to the minus 7. The unit is radian per second, right? To go to translational, because that unit is radian, if we multiply by the radius, we're basically taking that unit and we're replacing that with the radius, what it actually is, the number. So we're multiplying by that number, and the unit it's measured in is meters.
I have a question. Does that say 13,516.21?
Yes, 13,516.21 meters per second. So it's like we're going back to, I'm going to change my color of my drawing, otherwise it's getting messy. It's like we're going back up here in green, and we're actually plugging in a number here, and that number has a unit in meters. It's kind of like what we're doing, isn't it? Where we're saying 2 pi radians, it's like, well, what's the radius? Let's plug that in for radians. Isn't an orbit a revolution, not a single rotation? So shouldn't we need to multiply 2 pi r by 225? So the radius can replace by radius. Yeah, radius can replace the radians. That's to go to linear. Let me read this again. Isn't an orbit a revolution? Okay, I'm not going to be really good at defining the difference between what an orbit really is. I'm going to just stick to the intent of the question, because I'm not going to be able to do like an Earth and space lesson at all. I'm sorry. I know you probably know way more than I do about space, and I'm not going to be able to have a really good dialogue there. I'm sorry. Okay, that gets us through that problem. Let's scroll up and see what's on the next part of the page. And I guarantee you, practice on these, the experience in the problems will make the biggest difference. Okay, let's scroll up and see what we have. All right, this part of the page, this is, again, explanation of stuff we've already done. We've already done the translation of the formulas. Yes, they also included the this formula. It's totally valid. Use it. I don't care. I just didn't in my example because we were kind of getting the hang of it by then. No reason to beat the horse. Now, the next question underneath here, what must be true in order for these equations? What must be true for kinematics equations to work?
Acceleration must be constant.
Yes. Yes, your acceleration must be constant. We know our position's changing because we say delta x. We know time is changing because it takes time to do stuff, and that gives us a time. Velocity is changing. We say initial velocity being v naught, and we have final velocity. But what's one thing that has to be constant? Acceleration. Kinematics does not work unless acceleration is constant. So I'm going to go ahead and write that little bit in. Acceleration or alpha must be constant. Okay, got it. All right, let's see, sample problem 2. Looks like it has 3 parts, and then we're done with this page. Flying through this stuff. All right, let's take a look at this. What does it have for us? The disk in a, let's see if I can read it from here. The disk in a computer disk drive spins up from rest. Okay, I'm gonna write the things that are where we write out our given, our guess method. I'm not abandoning that stuff. So if it starts from rest, that means our omega naught equals 0 to a final angular speed. So that gives us me a final speed of, oh no, that's RPMs. I'm gonna have to convert that, but let's hold off. And then the time equals 2 seconds. What is the angular acceleration? So it wants to know alpha. Okay, well, if I've got 3 known variables, I can certainly solve for a 4th, but I need to get that third, what's that? Nope, okay. I need to get that third known variable, that omega. So let's convert this 54 5,400 revolutions per minute. Let's get that converted into something we can use. Remember, what do we want? Radians per second. That's what I need for omega to work. So let's start with revolutions. If revolutions is in the top, I'm going to put it in the bottom, 1 rev. And what can I convert 1 revolution to? I want it in radians. Can you give me something in radians?
Well, 2 pi
Yeah.
is the distance in 1 revolution.
Yeah. 2 pi radians is 1 revolution. So that works out. So now my revolutions cancel out. Now I can do this. Now I need to convert the minutes. So I need to bring minute to the top, 1 minute. It is 60 seconds. So my minutes would cancel out. And if I take 5,400, multiply by 2, multiply by pi, divide by 60, when I did that, I got 565.2, and I was left with radians per second as my unit. So I come back over here and I can plug in 565.2. Now I have
Sure, Watley.
Yeah, what's up?
So if we're like doing any conversions involving pi, do we have to like get a numerical answer? Can we leave our answers in terms of pi
For the
to make
most part,
calculations easier?
yeah, for the most part, you want to convert pi to a number.
Okay. Or at least if we can we hold off on that till the end of the problem?
Yeah, you may be able to. So if you want to hold on to pi for a little while, that's okay. Just know that if you've got like 5 pi plus 7, you would have to do the math then.
Yeah.
So just be careful with it. Make sure that you always keep like terms and all your math rules in place. But if you can handle it and you can juggle it, by all means, you can keep it as a pi as long as you want. You're going to see that I convert it every chance I get. But if you want to hold on to it, yeah, you can hold on to it. Somebody got a little bit different decimal. That's fine. It might be one of us used 3.14, one of us used the pi button. I did this math not today, so I'm just going to say, hey, we're not that far off of each other. I wouldn't worry about it. Let's take a look at it. Well, we've got our variables. We need to pick our formula. This looks like we can use what I'm going to call the WOTAT. So we've got this. Then the WO plus alpha T. We want to rearrange this to solve for alpha, don't we? So if I were to take this, subtract on both sides, and then divide by T, that would equal alpha. So if we want to just solve and say, how do we solve for alpha? We said it was a change in velocity over time. What's a change in velocity look like? Final minus initial. Okay, well, we can get to it either way. Now that we've got this, we can say that final is 565.2 minus 0. Well, that's still 565.2. Going to divide by time, which is 2 equals the alpha, the angular acceleration. When I divide by 2, that gets me what? I got 282.6 radians per second squared is alpha. There we go. All right, so that got me through that problem. I'm going to keep it in view because I feel like all this is a big continuation. It says at the end of 2 seconds, what is the angular displacement? What variable is it asking me for?
Theta.
Theta, yeah. All right, it's asking me for theta. So if I want to solve for theta, I can remember that theta is equal to the initial angular velocity times the time plus 1/2 the angular acceleration times the time squared. Okay, so the initial velocity was 0 times time is still 0 plus 1/2 times the angular acceleration I got in the previous problem, 282.6 times the time squared. The time was 2 squared is 4. So I've got that. Now I just need to put it in my calculator. When I did, I got back to the 565.2. And theta is measured in radians. Not too bad. Okay, very last step. How many revolutions is this? Now, earlier we went from revolutions and we were able to make a conversion. How did we converted revolutions to what? What did we use for that conversion?
Radius.
Our radians, yeah, radians. So we know that when we're looking at revolutions, if we've got theta, we're in pretty good shape. So we've got 565.2 radians, and we know that 2 pi radians is equal to 1 revolution. Radians cancel out. So 565.2 divided by 2 pi, don't do divided by in your calculator, divide by 2 pi like it's 2 times pi, because it's going to want to multiply it. So make sure that you parentheses your 2 pi in your calculator, or divide by 2, enter, divide by pi, enter. It's a bad way to make an error. We get 90 revolutions is what I got when I put it in my calculator. This revolution is the last unit that I've got on there. 565.2 divided by 2 divided by 3.14 gets me right about 90 revolutions. Okay, so we're going back. It's been a long time since we've done dimensional analysis, and it's been a really long time since we've done kinematics. So those skills are going to be coming back in. Do revolutions have to be a whole number? No, they don't have to be, because it might end up being half a revolution. Okay, so we've got that. Let's take a look at what else is going on today. Now in Canvas, I'm going to flip over to Canvas just ever so briefly. I tied today into next week. It just made the most amount of sense not to make a one-day week in rotation. So you can see today is a part of this week or next week. We've done the notes I gave you initially are only found in our classroom. They're not posted here because I would, it's for us. Now it is posted, it'll be posted in the video so you have access to them. We just did a page that was called notes. It had the practice problems. There is this kinematics reference. I haven't looked at it in detail, but page 1 has a ton of information. Page 2, the backside of it, if you were to print it, has some practice problems. And page 3 is repetition to page 2. It's a duplicate, but it's all solved for you. So you can kind of just look at it, use it for reference, use it for practice. Personally, I haven't looked a lot at it. So I'm not sure what questions I could answer readily about it, but it's a good reference. The last thing we have on here is rotational kinematics homework. That's what I want to get us started with and then let you finish going into next week. So let's go to that. Here's our homework. And let's zoom this in. There are 9 total questions across the page. 1 through 5 are on the front page, 6 through 9 on the back page. Let's take a look at this because some of these are conceptual. All of them are worth looking at. If you drive a truck with oversized tires, so you got Bubba with his big old truck, how will your speedometer be affected? And let's think of it, let's think of how, if you were to have a car and you went and bought bigger tires, what's going to be off about your speedometer? What do we think?
Well, your radius is going to be bigger because your tires are bigger.
Yep.
Which means your linear velocity is going to increase.
Okay, what about your angular velocity?
That won't change because the angle will still, because they're the same shape, they're just, the radius is bigger. So
right, because if you think about it, your car,
it's still a circle.
Right, it's still, your car is going to still think that every time it turns the wheel one time around, it's going to assume you've moved a certain distance. So if you're cruising at 45 miles an hour with big wheels or little wheels, your speedometer is set because it thinks that, well, if your speedometer is at 45, it's going to think, hey, that's so many turns of the wheel. So whether you've got a big wheel or a small wheel, if it goes around at the same amount, it has the same number of turns per second, they have the same angular velocity. Now the difference is, like you were saying, the difference comes in from the change of radius. If you get a bigger radius, you'll have a bigger circumference and you'll cover more ground. Therefore, you'll actually be moving faster than your speedometer indicates because of that radius, because you're taking the angular velocity multiplying by r. So here, I'm not going to spell it out because that's just boring, but I'll just kind of write out what we're saying here. And that is that you said it's about the radius, and you're absolutely right. Oh, somebody's coming in. I think they've already been here today. Pretty sure. Yeah. All right. So what we're saying with this person was we've increased the radius. And increasing the radius, each rotation will have it has that increased radius that's going to give us an increased displacement. So we're going to be moving faster. So speed. We end up with a higher velocity. Linear. Now, the increase in radius does not change the angular velocity. Increasing the radius does not change the angular velocity, just the linear velocity. Now, pressing the gas pedal is definitely going to change both. It's going to spin faster, that sort of thing. All right, after fixing a flat on a bicycle, you give the wheel a spin. If it rotates 3 times, through what angular displacement did the wheel rotate? Angular displacement, that's theta, right? Okay, so it's asking us about theta. It's asking us to solve for theta. So if it goes around 1 time, what's the angular displacement?
2
2 pi.
Yeah, 2 pi. And don't forget, it's in radians, 2 pi radians. So if we go around 3 times, what is it going to be?
6 pi.
6 pi radians. Yeah, no trick questions here. Come on, those come later. Just kidding. No, I'm not. All right, so 3 times around, that gives us the 6 pi radians. That is the angular displacement. All right, let's get to the real questions. Number 3, what is the angular velocity of the second hand on a clock? There's another question that asks for the minute hand of the clock. All right, angular velocity. We know that angular velocity would equal like a change in theta over time. Okay, so a second hand, when it does a lap, that's like 1 time around, right? And we said 1 time around is equal to 2 pi radians. And how long does it take to go all the way around? Like 60 seconds, something like that. So 60 seconds. If we do the math, we've got 2 times pi divided by 60 gets us like 0.105 radians per second. That's not too bad. All right, let's look at it for the minute hand. Again, we've got the same idea. We're looking for angular velocity, which is a change in theta over time. Here, it's still the minute hand, just it goes around once, every so often. So it goes around 2 pi radians. Now it takes an hour to go all the way around, right? And there's 3,600 seconds in an hour, 60 times 60. So this would be 3,600 seconds equals, let's see, when I did the math there, I got 0.00174, but it's probably better to write that as better to write that as 1.74 times 10 to the -3 radians per second. Okay, not terrible. Let's at least go through number 4. I think it has an A, B, C, D, and then I'll let you guys do 5 forward. How about that? So this one says an old phonograph. A phonograph's a record player, like old school record player. All right, record player with a radius. All right, it gives us some information. Let me write it in the, let's see, radius equals 0.2 meters. And it revolves at 45 revolutions per minute. Okay. Revolutions per minute, that is that's kind of like a speed, but it's not in the terms that we need. It's not in the units that we need it. So we need to make an adjustment. 45 revolutions per 1 minute. All right. We know that if revolutions on the top, we got to move them to the bottom. Revolutions, they cancel out. We said 1 revolution is 2 pi radians. That gets rid of revolutions, and we got radians. That's perfect. 1 minute, we can say that 1 minute on the top, so it cancels out, is equal to 60 seconds. So that minutes cancel out. 45 times 2 pi divided by 60 would get me 4.71. And I'm left with revolutions per second as my units. Well, let's see what the first question is. What is the angular velocity? Well, angular velocity is omega, and its units are radians per second. We've solved in radians per second over here, so we've already solved this one. It's equal to 4.71 radians per second. Done. That's cool. We did number one, or actually 4A. What is the translational velocity? All right, well, we know that V is equal to R omega. Okay, well, we've got omega 4.71. We got the radius 0.2. So this is 0.2 times 4.71, which equals, when I did this, I got 0.942 meters per second. Not too bad. I'm trying to leave number 4 totally on the screen as I move down though. Once a motor's turned off, okay, it takes, all right, now I've got a time that's equal to 0.75. It comes to a stop, so the final angular velocity is going to be 0 because it stops. What is the average angular acceleration? It's looking for alpha. Alpha's question mark. And we said that the initial velocity, angular velocity would be 4.71. Okay, well, if we're looking for alpha and we already, didn't we say like the final minus initial divided by time equals alpha? We said that earlier in one of the questions. We also said the change in angular velocity over time would be angular acceleration. So we've derived this formula at least twice today. So let's put it to work. The final is 0, the initial is 4.71, so 0 minus 4.71 would be negative 4.71. Divide by the time, which is 0.75. Do that little bit of math, and I'm going to come up with negative 6.28 radians per second squared. So I've got alpha right there. Lastly, it asked me how many revolutions did it make while coming to a stop. It's asking how many revolutions did it make when coming to a stop. Okay, well, revolutions, number of revolutions, the only way I've gone between revolutions is through radians, right? We were able to convert from radians to revolutions. So we can go from, we've gone from revolutions to radians, so we can go radians to revolutions, but we need radians. Which one of our variables uses radians as its unit?
Angular displacement.
Angular displacement, yeah, theta. So D is asking us for theta. It's like, hey, what's theta? And if we want to solve for theta, I can use theta is equal to initial angular velocity times time plus 1/2 acceleration or angular acceleration times t squared. All right, well, that's going to be a long sentence of numbers. So I've got what, 4.71 times 0.75 plus 1/2 times acceleration, which was negative 6.28 times time squared. Time was 0.75 squared. So 4.71 times 0.75, get that, add that to 1/2 times negative 6.28 times 0.75 squared. I'm sorry, it's long, but we've used that formula before and plugged in numbers. So I think we can do it again. We take a second, get that into our calculator. And when I get that through my calculator, let's see what I'm going to get. I'm getting 1.77 radians. Okay, I've got the number of radians. I need the number of revolutions. So I can say 1.77 radians and 2 pi radian is 1 revolution. Radians cancel. 1.77 divided by 2 pi, I get that equal to 0.28 revolutions. So we were able to solve it. Getting used to those conversions, getting used to how do I move from one to the other in dimensional analysis, and keeping in with using our kinematic equations. Now class gets out at 4:25. It is not even 4, it's a couple minutes to 4. So you've got like 25, less than 30 minutes, and all you have is 5 questions. Seems like a lot, but it's really not terrible. What I'm going to do is this. I want you guys to work on each of those 5 questions. Some of them you may be able to get real easily. Some of them you may get stuck on. If you get stuck, that's okay. You can skip to the next one, but attempt all 5 of them between now and Tuesday's class. There is no after-school tutorials today, nor on Monday morning. But Monday afternoon and Tuesday morning, you have 2 opportunities for tutorials, and I run both of those tutorials. So you can come in and you can get some help if you need it. When we start class on next Tuesday, I have an expectation that you've attempted each and every one of these questions. And as you have questions, I will provide answers. What I don't want to do is to work every single one of these problems for people that have not made attempts. Okay, take advantage of tutorials and take advantage of emailing me if you need some help. Okay, we'll start next class with question and answers, and then we're going to get into rotational inertia or moment of inertia next class.